Hello and welcome back everyone. In this part of the lecture, we will look at some laminar flows. But before we start, let me write down the Navier-Stokes equation. So the Navier-Stokes equation is given by this. Now the solution to this equation is often quite difficult because of this non-linear term over here. So this u dot nabla operator applied on the velocity field u. This is a non-linear term. And in general, any solution to Navier-Stokes, a generalized solution to Navier-Stokes becomes very difficult because of this nonlinear term. However, if we take certain assumptions, then it is possible to simplify these equations and then get their solution. So that's what we are going to do today. So we are going to look into some laminar flow solutions of Navier-Stokes by taking certain assumptions and dropping some terms out. So one assumption which is going to be common in all these cases is that the flow is fully developed. What does that mean? It means that there won't be any horizontal variation in the flow. So the flow will be invariance in the horizontal direction. So if this is my x direction, then del by del x of any quantity is going to be 0. So that's one of the key assumptions that I'm going to make in order to arrive at the solutions for the processes that we are going to look at today. There's one way we can visualize this assumption. For example, if we have a pipe and we go, so this is a pipe, and we go close to the entrance of the pipe, then of course on the two walls there is going to be no slip boundary condition. And if we apply a pressure P naught plus delta P from this side, then it will get some velocity U naught. But since this point on the walls, we are going to have a no slip boundary condition, which implies that U is going to be 0 over there, we will get a boundary layer which gets developed in such a fashion. So U will go from 0 to U naught over here. So it will be 0 in this at the boundary, but it will be U naught in the core. And what we get is then an entrance region where del by del x of the quantities will not be 0. So in this region, the assumption of a fully developed flow is invalid. And only at a distance x, which is far away from the entrance, from the starting point, we will get a situation where the flow is fully developed. So my first assumption would be to disregard any transients in the x direction, which means that I am already in a situation where the flow is fully developed. It is very important in fluid mechanics that we write down explicitly whatever assumptions we are taking in order to solve the equations. So this is one such assumption, which I said is a key assumption. So having taken those assumptions, let's look at the first set of problems. And the first one is a steady flow between parallel plates. Here we will have a boundary over there. So this is X, this is Y, and then we have a moving plate on the top, which moves to the right with a velocity u naught. And the gap between the plates is 2b, and we assume that it's a 2D flow. So we won't talk about the third dimension. We don't talk about the Z direction. And furthermore, we assume that d by dx of any quantity is 0. So let me call this invariance in x. So now with this assumption, if we look at the continuity equation, so the continuity equation is nabla of u is 0, which is del by del x of u plus del by del y of v is 0. U, by the way, is my velocity field, which is u I cap plus v j cap. So now if this term is 0, and this is 0 because of the the boundary because of the invariance condition that I have. Then I get del v by del y as 0. Furthermore, as per the boundary conditions, v is 0 at y equal to 0. And why is that? It's because at y equal to 0, we have a wall. So this is y equal to 0. And we have a wall, and the fluid cannot go inside that wall. So it's a no penetration boundary condition. So the liquid cannot penetrate inside the wall. So it's non-porous. So with these two conditions, what we get is that v is equal to 0 for all y. So we simply get that the velocity in the y direction is 0. So now if you look at the Navier-Stokes equation in the x and y direction, so in the x direction it will be del u by del t plus u del u by del x plus v del u by del y equals minus del p by del x plus mu by 1 upon rho over there, mu by rho del square u by del x square plus del square u by del y square. Again, with the invariance in x direction, we find that this term is 0. This term is also 0. Furthermore, from continuity equation, we know that v is 0. So this term goes away. We also assume that the flow is steady. So there is this is the second assumption, which is that the flow is steady, which means that any time derivative is also 0, which basically gives me the equation that del p by del x is equal to mu del square u by del y square. Furthermore, if we look into the y direction, then we have del v by del t plus u del v by del x plus v del v by del y equals minus del p by del y, again 1 upon rho over there, mu by rho del square by del x square plus del square by del y square v. Sorry about that. And again, with invariance in x, this one is 0. V is also 0, so we can quickly just cancel all the terms out, which gives me the equation that del p by del y is 0. So this means that p is only a function of x. It has no y dependence. So now what we have is that pressure is just a function of x, which means that the pressure gradient has no y dependence. So the dp by dx has no y dependence. Furthermore, del square u by del y square has no x dependence, and that's because we assume the invariance condition in the very beginning. So this tells me that dp by dx equals mu del square u by del y square. This is both equal to a constant. So it's called, let's say it's a, and where a is a constant, which further implies that I can integrate this equation twice to get u, which is nothing but y square plus cy plus d, where c and d are the two constants of integration. And now we can use the boundary condition, which is u equal to 0 at y equal to 0. This means that d is 0. And furthermore, u is equal to u naught at y equal to 2b. And if we plug that in, then we ultimately get the expression that u is equal to y u naught by 2b minus y by mu dp by dx b minus y by 2. And you can check if I plug in y equal to 0, then this term vanishes, this term vanishes, and then I get a velocity which is 0. And if y is equal to 2b, then this term goes to 0, but this term is goes to u naught. So this gives me y equal to u naught, and this one gives me u equal to 0. So that means that this equation is correct. Of course, I would want you to fill in the boundary conditions and then find out the same solution. But this is this is what you will get at the end. Now let us try and sketch these solutions. Of course, this solution will depend on the size or on the sign of dp by dx. Now imagine if dp by dx is positive. So what does this mean? So this means that the pressure increases in uh, the positive x direction. So if dp by dx is positive, it means the pressure grows from P naught to P naught plus delta P or something as we go towards to the right side. So if that happens, then of course we can show that the velocity will be 0 at two locations. One is of course the trivial solution, which is y is equal to 0, but will also be 0 at some point between the wall and the plate. So this plate which is moving with a velocity u naught, and the wall's velocity will be 0 twice. Once at the wall where y is equal to 0, and then another point somewhere over there. And you can think about it physically as well. So the velocity is u naught at the plate at the top. However, you have a higher pressure as you go to the right of the domain. So this one has a higher pressure. So you have a pressure gradient in this direction, which is forcing the fluid from right to left. Now, of course, this will win far from the top plate. So if you go further from the top plate, then this pressure gradient will win. And then you have a situation like that, so where the flow is from right to left. Whereas the closer you get to the top plate, uh, then the velocity of the plate, so the boundary condition which is set over there, that will win, and then you will have a flow from left to right. So that's how you can visualize it intuitively, that why there should be another stagnation point in the middle. Of course, you can find the location of this stagnation point by plugging in this u equal to 0. That I will also leave as an exercise. The second case would be when dp by dx is less than 0. So when the pressure gradient is negative, which means that we have a pressure gradient which is assisting the plate. So we have a higher pressure over there to the left, and we have a lower pressure on the right. So we have a pressure gradient which is assisting the flow. And in such a situation, we simply get a parabolic profile, which looks like that. So it's monotonically increasing until we reach u. There can of course be some special cases. So what happens if there is no pressure gradient? So if dp by dx is 0, then we get u is equal to y u naught by 2b, which is basically just linear velocity profile. This is also called a plane coed flow. It also means that the stress, the shear stress tau, given by mu del u by del y is constant. It's simply mu u naught by 2b. There can be another situation, which is the plane Poiseuille flow, where u naught is 0. So this is a situation where the top plate is not moving. If u naught is 0, then I will simply get u is equal to minus y by mu dp by dx b minus y by 2. And in this case, we will have a maxima of velocity at y is equal to b. Of course, at y equal to 0, the velocity will be 0, and also at y equal to 2b, the velocity will be 0. This is a special case again, where we have a solution. Okay, moving on. Let us now look into something called a circular Poiseuille flow. Sometimes this is also referred to as a tube flow or flow through pipes. So we are going to look into the case where we have flow through pipes. Setup of this process would be like this. See, we have a pipe of radius A, and then we will apply some pressure gradient from on in the system, which will induce some flow inside the pipe. And we will try to study this flow. Of course, we are going to again take an assumption that the flow is fully developed, so it's invariant in the x direction. The x direction is this one. Furthermore, we are going to solve this equation in the cylindrical coordinate system. So we are going to assume an r, theta, and x coordinate system instead of the common Cartesian or xyz coordinate system. So if you again use the same invariance in the x direction argument, and furthermore, if you think about the process, so what is going on is that we apply a pressure gradient on the left, and then we get a laminar flow in the pipe after a certain distance. So after the entrance transients have died out, so which will you can then argue that the u theta is zero. So there is no azimuthal component of the velocity field, and ur is also 0, which gives us that ux is non-zero, and it is actually a function of r. And this will satisfy the continuity equation. So you can plug these inside the continuity equation for cylindrical coordinate system, and then you will indeed see that it satisfies the divergence free condition. Furthermore, the azimuthal Navier-Stokes will give that dp by d theta is 0. So p is not dependent on the azimuthal angle theta. And the radial Navier-Stokes will give an equation which says that dp by dr is 0. So that this pressure does not depend on the r direction either. And the x momentum equation is del ux by del t plus this guy equals y1 by rho del p by del x plus mu by rho del square ux, where the operator del square is 1 by r del by del r of r del by del r plus 1 by r square del square by del theta square plus del by del x square. Of course, this term is 0, and we can argue further that this term, so we also assume that there is no azimuthal variance, and that's that we can also justify that physically by looking at the system. So this part is also 0, which basically gives me the final form of this equation, which is 0 equals, of course we are going to assume a steady flow, and you can also do some calculations and show that this part is also 0. So we get 0 equals dp by dx plus mu by r del by del r of r dux by dr. Similar to the flow between parallel plates. So if you take an analogies between this condition and the condition where we studied the flow between parallel plates, you can again see that this term of the equation is not dependent on x. So this term cannot depend on x, so it should be a constant, which means that I can integrate this equation twice, which will give me the following equation. So if I integrate it once, then I get a is equal to, and if I divide this equation by r, then you get a by r equals, now integrating again, we get a, l, and r, and then we can apply the boundary conditions, which are that at r equals 0, the velocity is finite. So this implies that A should be 0, because if A is not 0, right? So at R equal to 0, if A is non-zero, then ln R will tend to infinity, and we cannot have an unbounded solution. So of course this A has to be 0. So this is the first boundary condition that we can apply. The second one is that at R equals A, U is equal to 0, and this will give me that B is equal to minus A square by 4 mu dp by dx. And once we plug this in, then we get U is equal to R square minus A square by 4 mu dp by dx. So now we have another solution to the Navier-Stokes equation. Let us go on and calculate the flow rate. So let's assume that Q is the flow rate through the pipe. So more often than not in such problems, we are either given a pressure gradient. So we know the pressure gradient, and then we want to calculate how much flow is passing through the pipe, or we know the flow through the pipe, and then we want to know the pressure drop across the pipe. So let's try and calculate what this what this flow rate should be. So the flow rate can be defined as an integral of u r d theta dr. So integrate over theta from 0 to 2 pi, and then integrate over r from 0 to a. And then if you do that calculation, you get q equals minus pi a to the power 4 by 8 mu dp by dx. So you can see that this q is proportional to a to the power 4, which is quite a strong dependence. So if I reduce uh, the radius by 10%, then the flow rate reduces by 35%. So it's quite a strong drop in the flow rate. All right. So all the cases that we have studied so far were steady state cases. Now let us look at a couple of cases which have time dependence, so which are unsteady in nature. So before I dig into the cases, let me show you a video. So here we have an impulsively started plate. So what is that? So there is a plate which is at this location over here. So if you can follow my cursor, and then this person is going to mark a die on a sheet, and then suddenly this plate will start moving. And as you can see from the location of the die, that there is a certain lag between the time at which the plate starts to move and the time at which the fluid particles inside this in the bulk over here feel the presence of this motion and then respond accordingly. So we are going to look into this case now. So this problem is also known as Stokes' first problem, and the system setup is something like this: that the velocity field for all x comma y, but for time t is equal to 0 is 0. So at time t is equal to 0, everything is at rest. Note that we are going to again assume a 2D geometry, just for the sake of simplicity. Now at time t is equal to 0 plus, the velocity at y equal to 0 is u naught. So at t is equal to 0 plus, I suddenly give the bottom plate a push such so that it starts moving with a velocity u. And then as we saw in the video, what will happen is that the fluid parcels in the bulk will respond to this impulsively applied velocity u. Let's call it u naught. And then a flow will develop in the bulk. So we will try to find out this velocity profile u as a function of y. So these conditions, they describe the flow properly. Now one thing which I'm going to assume once again is that the flow is invariant in the x direction. So I'm again going to assume that del by del x of any quantity is 0. I can make this assumption by assuming that the plate attains a velocity u naught before the bulk. However, I'm going to ignore any initial transients. So although this is an impulsively started plate, nonetheless, I will still assume that the flow is invariant in the x direction. And what follows from this assumption is the fact that del v by del y will also be 0 because of the continuity equation. And as we know from the boundary conditions that the plate has a non-penetration boundary condition, so the plate is impermeable, and therefore the velocity at y is equal to 0. So the velocity in the y direction at y equal to 0 is 0, which implies that velocity is 0 for all x comma y. So this velocity v, the v component of the velocity is 0 for all x comma y. And then if I write out the x momentum equation, I will get the following. So the derivation is not different than what we have been doing so far. The only difference is that it's an unsteady flow now. So del u by del t will not vanish. So you can also try this as an exercise, and then let me know if you don't reach this x momentum equation. Similarly, the y momentum equation will simply read that del p by del y is 0. Now, something that you might notice here is that this is an open container, so it's not closed. So the pressure, velocity, uh, all quantities far from the plate is always going to be 0, since this is an open container. All right, which means that if the pressure del p by del y is 0 uh, because of the y momentum equation, and that the pressure is 0 at far from the plate, and as it is an open system, the pressure gradient, so del p by del x, will also be 0, since we are talking about an open container. So this makes our life a bit easy, because now this pressure gradient also goes off, and what we are left with, it is a simple equation, well, simpler equation I should say, which is this. Now, unlike the previous cases, I cannot integrate this equation, and the reason being that u is a function of both x as well as time. So so I cannot integrate this particular equation. But I do know the boundary conditions, so let us write it down. So the boundary conditions for u will read that u at y equal to y and time t is equal to 0 is 0. U at y equal to 0 for any time t is u naught, and u at y tends to infinity at any time t is also 0. So this is the far field boundary condition. The rest two boundary conditions you already know. So in order to solve this equation, I'm going to use something called a similarity solution, which is basically a fancy way of saying that I will use dimensional analysis to try and find some suitable solution to this partial differential equation. So we know that this velocity u is a function of u naught, the spatial coordinate y, time t, and the kinematic viscosity, that is mu over rho. We can write it as nu. So now if we go on and use our dimensional analysis knowledge, then we will find that we can rewrite this functional equation as u over u naught is a function of y upon square root nu times t. So this, again, I'm going to leave as an assignment. So you should try and follow the same steps as we did before, and you should be able to reach this particular equation. We can just do a quick check over here. U has a dimension of meter per second. U naught, of course, is also a speed, so it also has a dimension of meter per second. So this part has a dimension of unity. Inside, we have a kinematic viscosity, which is a dimension of meter square per second, time t, which has a dimension of second. So over here you get meter square, and then square root you get meter, and then y has a dimension of meter. So this also has a dimension of unity. Y upon square root nu t is referred to as a similarity variable, and sometimes it is also called an ANSAG. Now let us define another variable eta, which is y upon 2 times square root nu t. So now our functional reads u upon u naught is a function of eta. Now something interesting will happen if we plug this functional in our partial differential equation. But before we do so, we need to find the different terms that are present in that equation. So let's try and find these values. So del u by del t is nothing but u naught times del f by del t, which is nothing but u naught times df by d eta. So now it's a total derivative, not a partial derivative, times d eta by dt, and del eta by del t is nothing but minus 1 upon 1 by 4 times y by square root nu t to the power 3 by 2. So if we plug this in, then we get del u by del t is nothing but minus u naught df by d eta times minus 1 by 4 y upon square root nu t into 1 by t, which can be simplified as minus u naught f prime, where f prime is df by d eta, into eta divided by 2t. Now del u by del y is nothing but u naught times del f by del y, which can be simply written as u naught times df by d eta times del eta by del y, which is u naught f prime 1 upon square root nu t. So del square u by del y square will be u naught f double prime 1 upon nu t times again del eta by del y, which we know from the previous equation is u naught f double prime upon nu t. Oh, I missed a 2 over here. So there is a 2 over there, 2 over there, and so this becomes 4. So now if I plug these terms back into the equation, what I get is minus u naught f prime eta upon 2t is equal to nu times u naught f double prime upon 4 nu t. And we can cancel a few terms. So t goes out, nu goes out, we can cancel this, u naught goes out. So finally, the equation which I get is f double prime plus 2 eta f prime is equal to 0. So now this is an ordinary differential equation which we can solve. So we can solve this equation if we put in the appropriate boundary conditions. So the boundary conditions are these. Now let us try and figure out what these boundary conditions will be in the new f and eta space. So eta is nothing but y upon 2 times square root nu t. So for t is equal to 0, eta will tend to infinity. Also for y tends to infinity, eta will also tends to infinity. And we see that for both these cases, the velocity is 0. So this gives me the boundary condition that f at eta tends to infinity is equal to 0. Furthermore, if y is 0, then eta will be 0. So f at eta equal to 0 is equal to 1, since f is nothing but u over u naught. So now we have these two boundary conditions and we have an ordinary differential equation. So this should be easy to solve. So let's try and solve it. So we have df prime by d eta is equal to minus 2 eta f prime, which gives me this. So on integrating once, I get log of f prime is equal to minus eta square plus c. We can write it as f prime is nothing but a times e to the power minus eta square. So from here, f will be a integration 0 to eta e to the power minus eta square d eta plus b, where a and b are the constants of integration that we need to figure out by using the boundary conditions. So as we know, the first boundary condition reads that f at eta equal to 0 is 1. So at eta equal to 0, of course, this integral will be 0. So we get b is equal to 1. Next, we see that f at eta tends to infinity is 0. So we get 0 equals a times integration 0 to infinity e to the power minus eta square d eta plus 1. And this you may recognize this function as some sort of error function. This will give, so from, and for integration from 0 to infinity, I will get a times square root pi by 2 plus 1, and if this is 0, then a is nothing but minus 2 by root pi. So if we plug the value of a and b into our equation, then we get the final form of f eta, which is nothing but 1 minus 2 by root pi integration 0 to eta e to the power minus eta square d eta. Of course, if we define the error function as 2 upon root pi 0 to eta e to the power minus eta square d eta, then this function fn is nothing but 1 minus error function of eta, which I can write as u upon u naught is 1 minus error function y upon 2 square root mu t. So now let's go on and plot this equation. So on the x-axis, I will plot u upon u naught, and on the y-axis, I will plot eta, which is y upon 2 square root mu t, and then I get a velocity profile which looks like that. Y equal to 0, this velocity will be 1. And then what happens here is that all this is one unique velocity profile which I get because I solved this ordinary differential equation in f and eta space, and then I get one unique velocity profile. Of course, for different t and different y and different u naught, you might get different curves, but all these curves will collapse on one single unique line. And this is one of the interesting features of similarity solution, that you can describe the entire process by just getting one unique solution. So now we looked into the solution of this Stokes first problem. Now let us try and visualize this solution. So here I have a mathematical notebook for you, which is already on canvas. So just to remind you all that the plate at the bottom is moving with a constant velocity u naught. Over here, we can put this constant velocity as 4. And then what we find is that with time, this plate moves at a constant velocity. So the trajectory of this plate is just a straight line. which is over here. And now we can try and visualize the velocity profile over the plate. So on this graph, on the y-axis, we have the y coordinate of the system, and on the x-axis, we have the u. So this plot is very similar to the one which we just saw, but now this is in y and u space. And as we can see, at t is equal to 0 plus, the plate is already moving. So the plate already has a velocity u naught, but the rest of the fluid bulk is not moving. The rest of the fluid bulk is at rest. And then if I increase the time, then you see the flow being developed in the bulk. And as t tends to infinity, we will just be left with a vertical straight line. And that is because the entire fluid bulk is now moving with the plate. So this is the problem of the impulsively started plate. So you can see how this plate starts to move and then the fluid bulk follows. So after visualizing the velocity profile, we can also integrate the velocity over time to find position. And then we can visualize it by using a line of die at x equal to 0. And if we play it, you get the location, the position of this die at different time instances once the plate has started moving. And if you remember, I showed a similar video in the very beginning of the lecture. So let me just remind you of that video. And here also you saw that this die was advected with the flow. The only difference between this case and the case that we solved is that in the experimental video over here, the plate is moving from right to left, whereas in our visualization over here, the plate is moving from left to right. And we can, of course, take a stroboscopic image, different stroboscopic images of this die, and then we get an image which looks like this, and time increases in this direction. So this mathematical notebook is available on Canvas, and I would like you to play with this and try to get deeper understanding into the physics of this problem. Okay, so moving on, let us look into Stokes' second problem. So the setup is very similar to what we had for the Stokes' first problem. The only difference is that this plate now moves with an oscillatory velocity profile. So instead of moving in one direction, this plate oscillates with a velocity which goes as u naught cos of omega t, where omega is the frequency of these oscillations. So the boundary conditions will read as u at y equal to 0 at any time t is u naught cos omega t, and u at y tends to infinity at any time t is 0. So this is again the far field boundary condition, and this one is the boundary condition for the velocity at y equal to 0. Moreover, the partial differential equation also remains the same. So if you follow similar arguments as you did for Stokes' first problem, you will again reach the same equation. But what changes is the way we are going to solve this. So even though we have the same equation of motion as we had for the Stokes' first problem, nonetheless, we cannot use the same similarity solution as before. And the reason is this cos omega t term over here, where omega is, as I said before, is the oscillation frequency. So in a steady state, the flow variables must have a periodicity which is equal to the boundary condition periodicity. So if the plate moves with a frequency omega, then so should the velocity profile inside in the bulk of the liquid, which means that we can use a complex guess for our solution. So we can use this particular ansatz, which is that the solution will be the real part of some function of y times e to the power iota omega t. And this is in order to fulfill the boundary conditions oscillations frequency omega. So now if I substitute this equation, this functional, back in the partial differential equation, what I get is iota omega f is equal to nu times d square f by dy square. Of course, I'm going to drop this condition for having the real part of the solution until the final stages of the solution. So now we have an ordinary differential equation, and the solution of this equation will have harmonic oscillations. The solution will be of the form that f is equal to exponential of ky, where k square is iota omega by nu. So this is the part of the harmonic oscillators, and k is plus minus iota omega by nu square root, which gives that k is equal to plus minus iota plus 1 square root omega by 2 nu. So if we plug this in, then the general solution of f will read a exponential of minus iota plus 1 y square root omega by 2 nu plus b exponential of iota plus 1 y square root omega by 2 nu. But of course, we should have a bounded solution in y. So if this term will exist, then the solution will get unbounded in y, and therefore b should be equal to 0. So this is where we apply the first boundary condition that we had. And so the f that we get is a exponential of minus iota plus 1 y square root omega by 2 nu. And once we plug this in into the final solution, which is u y comma t, is the real part of f y e to the power iota omega t. If we plug this in, and after some mathematics, and also applying the boundary condition that at y equal to 0, f should be equal to u naught, we get that u at y comma t is u naught exponential of minus y square root omega by 2 nu times cos of omega t minus y square root omega by 2 nu. Now let us try and visualize this solution. So here at t is equal to 0, we have a situation like this. So the velocity profile at y equal to 0, so the velocity at y equal to 0 is u naught cos omega t, and this velocity oscillates also with y, but it also decays. So it actually looks like a dispersive traveling wave in the y direction. So it resembles a dispersing traveling wave in the y direction. But you should note that there is no restoring force in the system. So it's not really a traveling wave. So these oscillations are simply because of the oscillating velocity profile that we have. And then as time progresses, we can visualize the velocity profile, and we can do something similar as we did for the other case, is to put a die, and then we also see that this die also oscillates about the origin. But one thing that we can also notice is that these oscillations are not symmetric. So you can see that these are asymmetric oscillations. And this asymmetry comes from the fact that we released this die at x equal to 0. And depending on the location or the position of this die and its initial shape, this asymmetric shape can be different. So one thing that you can do is to play around with it and then release this die at different locations and try and see what result you get.